Well, hello friends. Welcome back to the program. Today we are going to work on kernel stuff in Serenity, and I have a test case that I would like to make faster. So it is this, find slash. And of course what find slash does is that it will iterate through the entire file system and print out every directory and file that we have. And I want that to go faster because currently if we time it, it takes, let's do a couple of times here just so we get a feel for it. So we're around 900 milliseconds, 1 second, something like that, just to loop through the file system and print out everything. And I think we can do a lot better than that because I know that there are silly things happening, silly bottlenecks and stuff, but I never really sat down to work on them. I've just been aware of them peripherally for a long time. So today we're gonna take this seriously and try to improve the situation. So of course, the first thing we'll do is we'll just grab a profile and then take a look at what is going on. So opening this up, we can see that 97% of runtime is in the kernel as expected. And most of it is in either stat or open. And if we look in stat, we can see that it is doing a metadata lookup in the virtual file system, which leads into path resolution. And then in path resolution is where most of the time is spent. So this is something that we've known for a long time. Path resolution on the system is slow. And if we look at what makes it slow, it is partly that looking into the ext2fs driver, we have some time spent in there. So doing a lookup of child inodes takes one chunk of the time. And then we also have custody allocation, which is dominated by string allocation, actually. So this part right here, I think, is probably the most obvious how to avoid. So we should start with that. And then we can look at one thing at a time, really. But I think the fact that custody allocation has 12% of total runtime in just creating kernel strings is that's our entry point here. So I guess we should talk about what a custody is. So a custody is a kernel object in Serenity that represents the relationship between a directory and one of its children. So it's basically a directory, the name of a child, and then the inode of that child. And when you do a lookup of a path in the system, what you get back is, well, either you get an error saying, oh, this file does not exist, or you get a custody. And the main reason that custody objects exist is that many file systems don't actually encode with the parent of a file. So if you have a file, you don't know, by just looking at that file on disk, you don't know which directory it's in, if it's even in a directory. There's no way to divine that from just looking at the file. So because during path resolution, we actually work our way from some starting point through the directory tree, eventually finding the file, we want to hold on to that information. So like, what were the parents of this child? Because it's then later very useful information to us. For example, if you ask the kernel, what is the path of this file? Then we can walk backwards through the custody chain and work out the path that way. So that is sort of what the custody object is about. So if we look at the members here, we can see that it has a parent custody. That's the directory that owns this custody, or that this file is in. And then it has a string name. So this is the name of the child. And then it has an inode, which is the inode of the child that we are pointing to here. And then it also has mount flags, which are supposed to keep track of, like, if you cross a mount boundary during path resolution, then we have to make sure that the custody is aware of the mount flags that are in effect at the mount point that the inode is in. And that's a little bit iffy, but and I'm not sure that the factoring is the best, because maybe there would be a better way to do that. But at the moment, we have to keep track of the mount flags of wherever we are in the file system. So now that I've told you about custody, we can talk about the situation here. So if we look at how path resolution works, so let me actually draw that for you here in Vim. So say that you want to resolve the path etc passwd, right? Etc password. What happens if you tell the system, hey, open etc password, then we go into path resolution in the kernel to figure out, okay, well, what file is this referring to, right? And what we do is we break this thing up into parts or segments, and we just split at the slash characters. So first we start at the root, and then we look for something called etc. And if we find that, then we go in there and look for something called password, right? So that's the basic idea of path resolution. You just split this string into parts and then start at the root. And if there's no leading slash, of course, we start at the current directory or whatever relative base we're supposed to be using. So there are some APIs that allow you to specify a relative base, but that's the general idea of it. And then, of course, as I was saying, what you would get back here, assuming we do find the file, is a custody that has a parent etc, and it has a name, password, and it has an inode, the password inode on disk, right? That's what you get back. And then this guy right here points to another custody, which is custody with a parent of the root. And the name is etc, and the inode is the etc inode on disk. And then, of course, there's also a root custody, which is always cached by the file system itself because we keep using it. It's part of every resolved custody chain because everything starts at the root ultimately. Anyway, so here what's going on is that whenever we do path resolution, we will create new custody objects, right? So path resolution always leads to the creation of a new temporary custody object that is used to describe the relationship between the parent directory and the child file that you just resolved the path to. But when you're done with this thing, you just throw it away. And this is definitely suboptimal because it means that we have to keep creating these over and over, and very likely we are creating more of these than we would need if we had some way to realize that, wait a minute, we already have a custody object for this thing. I'll just give you that. And that's what we're going to start with. So basically, we want this thing to have a cache. And I think the easiest way to build this cache is to just make a list of all the currently existing custodies. So we'll put that into a singleton. And we're going to make a simple intrusive list. And then we need to have an intrusive list node of, let's see, I always forget how this works. Intrusive list node to custody, and we'll call it the all custodies list node, or maybe just list node. or no, m all custodies list node. And then what we normally do is we have a public thing where we create a type def like this. And it would look something like this. So intrusive list to custody with a raw pointer. So the list is not going to own or reference these things strongly. It's going to be weakly owned. All custodies list node, right? We can even call this all custodies list. And then we will make a singleton of those. So singleton of custody, all custodies list. And actually, we should make this protected by a spin lock, let's say. So let's use spin lock protected value. And this will be a singleton of spin lock protected value. All custodies. Actually, I guess I can just do this. And then make a getter for it. So the getter will be like this. All custodies. Okay. So now we have our spin lock protected all custodies list. And let's just make sure that we add custodies to it, or that we look through it when trying to create one. So try create, we'll now have to look through the existing custodies first. So we'll do all custodies with, this is a new API we have for spin lock protected value. So the way this works is that you have to access this list via calling with on the spin lock protected value container. And it ensures that you cannot access it without taking the lock. So this is pretty sweet, actually. So we'll do like this. And then I guess we'll just iterate through the list here and see if custody dot. Yeah, so we're not going to have any fancy hashing or anything at the moment. We'll just do a simple scan. And then this could definitely be extended with hashing later, but for now we're just gonna do a scan and compare here. And let's check that the mount flags are identical as well. Yeah, so it's just a straight cache. If that's what we find, then we return that custody. And then the with function has a really nice feature in that you can return something from it, and then you can just wrap your whole thing like this. I really like this. So you just say in here that your return type is whatever this function wants to return. And then it just handles the returns for you. It's super, super nice. And then this entire function is now wrapped in a scoped spin lock. So we're holding the lock throughout this entire function. So I guess if we didn't find it in the cache, then what we want to do is create it as normal. And then by the end here, we'll simply do all custodies. We have it here. It's called list, actually. Maybe we should call it all custodies just to be clear. Append custody, right? Yeah, so now all custodies is on the list and we should be good. And then we want to remove these from the list, and it's not quite good enough to do it in the custody destructor because If you do that in a custody destructor, there's a race where somebody else might go and iterate the all custodies list at the same time. Right when you think you're about to destroy a custody, somebody goes and manages to lock this list before the destructor does, finds your custody and takes a strong reference to it. And now the destructor will continue running later on, but it will destroy a strongly referenced object, and that will create chaos. And we do not want chaos. So the solution we've come up with for situations like this, actually just yesterday, is to inherit from ref counted base instead of ref counted, and then provide our very own unref implementation. So we have to implement our own unref. And what unref does normally is that it just decrements the ref count, and then if it gets to 0, then it will call the destructor, or call delete on this. But what we're going to do is, let's see, if auto remaining ref count is dref base. So dref base will decrement the ref count by 1 and return the new ref count. And if it returns a non-zero value, then we just want to return false, because that means that we didn't destroy anything. And I think we want to do all of this with the all custodies list lock held. So we don't need to actually touch the list, we just want to lock it. So we'll do that. And then return true. Let's see, so bool did reach 0, or let's call it should destroy. Yeah. Right, so we're decrementing the ref count with the list lock held. And once we return from here, we know that there's no way that somebody has added a ref to it so that we can't destroy it anymore. So if we return from here with true, then we should be good to destroy the custody. And of course, in order for that to work, we have to delete ourselves from the list here. So I guess actually we do need the list. All custodies, remove this. There we go. And then drops const qualifier. Oh, interesting. So I guess we can also do it this way, remove, right? And then we make it mutable, and then we don't need that. Yeah, so one thing that's nice about having our intrusive list is that you don't actually need a pointer to the list head or the list object in order to remove something from it. You can call remove directly on the node, and the node knows how to find its way there. And I guess we can just say like this. If dref base is non-zero, then return false, right? Yeah, and of course the reason that we call the destructor here instead of in here is that we don't need to like keep the custody list locked on this thread. If somebody else wants to use it, because once we've taken ourselves out of the list, there's no way that somebody can accidentally find us. So let's see if this would just work. Actually, let's print here, cached custody, found cached custody. So we had a custody cache a very long time ago, but it was not correct, and it didn't work correctly. It had a lot of, it kept crashing and stuff. I think it was like a simple hash table or something that didn't even compare all of the inputs correctly. So I removed that like over a year ago or something like that. So today we are coming back to this and trying to do things correctly. So it seems like we have some, we're definitely hitting this code path, so that's good. Obviously the debug statements here are going to trip up any kind of timing that we do, so we have to remove those before we can time those. But just to get a general feel for it, what this might give us in terms of improvement. So let's see. The first run is cold, so I'm just going to ignore that. All right. So already somewhat of an improvement, right? Because when we started, we were around 900 milliseconds to 1,000 milliseconds. Now we are dipping like below 800, somewhere in 750 to 800 range, even 700. So already quite promising. Let's get a profile with this change. And I think that was 43 that we just made there. So find 43 and see what we're doing now. So of course, still basically all time spent in the kernel, stat, metadata lookup, file system, path resolution, just as before. Although now we can see that custody try create has moved down here quite a bit. And we don't have any, we don't see like k-string, kernel string allocation anywhere near the top here, that's really positive. So I'm guessing that, yeah, here it is actually. So it's down from 12% in string allocation to 7-ish. So I would say that seems like a good improvement already. And let's see. The time that we spend in custody try create now actually is in the spin lock destructor. Oh, right, because I think when we take the spin lock, then we're no longer able to profile what goes on in there. I think the spin lock probably disables interrupts, right? So that's kind of unfortunate. I think Tom has a patch in the works that stops spin locks from disabling interrupts so that you can still handle IRQs and stuff while you're in spin lock region. Or I don't remember exactly, but it would be very nice if we could, because this is very frustrating when you're profiling something in the kernel and it just tells you, oh, you were in a spin lock, or you held a spin lock here, so you can't know what you were doing. That's obviously a bit sad. Also, what the heck is this? procfs process subdirectory inode lookup. Why is that so slow? Lookup file descriptions directory. Huh. So we're in procfs doing stuff. And it's definitely taking time there. So there's probably something that we could do less of. procfs lookup. Wait, what was it called? Process subdirectory inode. Lookup, what does it do? What was calling through to lookup file descriptions directory, okay. And then this guy calls file descriptions enumerate, sure. Why is this so heavy? It will go through all of the file descriptions in a process to do what? Wait, now I'm curious what this is actually doing. Okay, so we are enumerating those, and then we create inodes for each file description. Oh, look here. That's so gnarly. We are checking if the name is a given number by creating a string. So, oof. Well, this can definitely be better. So we're creating strings for like the numbers 0, 1, 2, 3, 4, and then comparing them against a name. What on earth? This is so weird. Because we definitely have like a way to convert this to a number instead, which is allocation free. So we should probably do that. So let's say to uint. Let's say name number is name to uint. Why are you suggesting template to uint? And then I guess we should use this fancy new way of calling these maybe number. If maybe number has value and maybe number value is count. Look at that, no temporary string creation. I feel like that's probably going to help a bit. Let's see how we do without that allocation there. Also, do we have any more of these in here? String number. So I guess these require a string. Oh, look at these. So we have one of those that we can get rid of. Okay, so timing that. Oh, look at that, we're in the 6s. Okay, so definitely nice. Let's take care of this one here as well. So auto maybe number is name to uint. Oh, and then we want to check against this actually. So I guess we should use an int. Oh, actually, I think you can even compare. I think we can compare optional against t now. Somebody added. Yeah, and it automatically does a value check. So if you have a value in your optional, that you can compare it against the stored type directly. Who added this? This is so neat. Max. Enable direct comparison of optional t and t. That's so cool. I love that. Thank you, Max, for adding that. Let's use it. We don't have to write our code this way. We can even just say like if name to int equals tid. Oof, that's juicy. That's so good. And we can do the same thing here. Name to uint equals count. I love that. That's so good. Let's see if that second string to number or number to string conversion was hurting us. 750, 700, 679. Look at those. Look at those. Very good digits. So let's reprofile here. We don't need time. And let's see, what was this? 38. So fine, 38. Okay, so what are we doing now? We're still in a stat. Resolve path. Now we have ext2fs lookups. Sure. So looking up, lookup is a thing that you can call on an inode. So it's a virtual inode function. where you call lookup on a directory inode to ask it like, hey, do you have a child with this name? If so, give me that child inode. And then we can see here the try create sort of bubbling up a little bit here. Of course, as you remove other things from the profile, then remaining stuff is going to start to bubble up. And we also have metadata lookups for ex2fs. That's fine. sysfs inode metadata. It's just 1%, but I'm curious, why is it even here? Wait, what's going on here? PCI device attribute sysfs component. Try to generate buff. Wait a moment. This looks to me like we're looking up the size of something in sysfs, and in order to tell you what the size is, it's forced to generate the file. So let's go look at it in the file system. So that would be in sysbus pc. No? Oh, it's in PCI? Oh, maybe that should be in sysbus. So let's go into one of these directories here. And yeah, look at those. They all have a size. So that if you call cat class, then you see the content. But we don't need to expose the precise size that you would find if you would cat the thing. It's fine to just return 0 for those. I think we're probably doing unnecessary busy work computing the size here. So let's see how that works though. So PCI device attribute sysfs component size. Oh, that's some sad stuff. So it will generate a buffer, and is it cached? It's not even cached. Oof. So complete waste of work when we can also just return 0. Boom. So let's totally do that and nuke some unnecessary work. Because the thing is that it's fine to say that a generated file in the file system has 0 size, because if somebody opens that thing, tries to read from it, they will still try to read. The size is not going to prevent you from seeking through the stream. So if we go to this PCI something something, so now these all have size 0, but if you cat class, you can see that it still has 3 bytes in it, just that the size here does not reflect that because it doesn't need to. And we don't need to compute that. So I think that's probably healthy. So let's do a little bit of timing. Ooh, look at those numbers. Now we're in the 660 range. 650. Ooh. This is going really well so far. Let's see. Take a new profile. And take a look here. So what are we doing now? Stat still dominating, although we also have the open syscall. And of course, if we look into open, we see that it is also doing path resolution. So not terribly fascinating. Although it's interesting to note that that during path resolution, we do metadata lookups on inodes. So even by just doing path resolution in sysfs, we were generating PCI device attribute content just so that we could tell you the size of it. So it's a bit weird. Why do we do metadata lookups? Probably because we want to look at permissions and stuff like that. I guess that's probably what we're doing with it. But nothing terribly fascinating going on in the open syscall, just more path resolution. And then we have get dir entries, which is our directory iteration thing. That's just 2%. So path resolution is the big ticket item. Actually, maybe we can find it here as a top level item, because I'm using top functions in the profiler, which takes every subtree and hoists it so that every possible subtree is a root node. and that allows things to sort of coalesce across subtrees so that you find, even though resolve path is called, it's called by both the stat and open syscalls, and path resolution is like, it's nested within stat and open, but because it's so hot within both of them, you can find it at the top of the top functions listing here. So it's a very, very useful tree transformation for profiling. So if we look at this view now, we can see that what dominates path resolution is ext2fs inode lookups. I guess that's kind of expected. And we have the process subdirectory inode lookups, lookup file descriptions directory, enumerable. Yeah, but these are now in like the 1-2%, so that's not nearly as bad as it was before. So that's good. Although I think one thing that's going on there actually in lookup file descriptions directory. So, or no, I was thinking we're creating an inode. So the proc file system creates inodes on demand, but only if it's the inode that you're looking for. So, I mean, that is okay. That's what it's meant to do. Try to exit the loop earlier. Oh, that's a good fix me, actually. We can definitely exit the loop earlier. Like if we find what we're looking for, we could bail out instead of keeping going. But I don't know, let's not overthink it when we have bigger things. So first thing we're going to do now actually is some commits, because I've accumulated a handful of patches here. So let's see. Right, so the PCI stuff in sys, let's just commit that. Also, that makes me wonder if we have other similar things elsewhere. So where was that? Here, size, so component size. There's only one of those. Who do you inherit from? sysfs component, public sysfs component. What is the default behavior of size? To return 0. Okay, so we can even remove the subclassing of that thing, or the override. We didn't even need it. Default behavior is good enough. Simplification all the way. But who else was inheriting from this? Let's see if somebody else is doing sysfs component. So do you have size? You do not have size. Do you have size? No. How about you? No. Okay, so nobody overrides the size. That's good. Okay, so let's see. Kernel, sysfs. Don't compute size of PCI files in sys. Yeah, let's just say that. So there's no need to, or there's no need for generated files in sysfs to tell you their precise file size when you stat them. I noticed when profiling find slash that we are spending a chunk of time generating and throwing away sysfs content just so we could tell you exactly how large it was. How large it would be, yeah. Yeah, because we don't need that. Okay, and then let's also do those two number to string conversions that we found in procfs. So kernel procfs avoid unnecessary number to string conversions. We don't need to create a new string from a number in order to compare an existing string to that number. Converting the existing string to a number, it's much cheaper since it does not require any heap allocations. Ran into this while profiling find slash. Okay. And then we have our custody changes. So basically what we're doing is we're just remembering all the live custody objects. Do note that the custody cache that I'm adding here is a weak cache, right? So it does not strongly retain live custodies. So when a custody goes out of scope, the cache is not going to keep it alive. So this cache only works while somebody's keeping these alive. If they go out of scope, they go away. So it's nicely automatically garbage collected like that. There might be a use case for like allowing the custody cache to retain like a bounded number of unused custodies, like most recently used custodies or something like that, so that looking them up would be fast even if they go out of scope. But that's beyond the scope of this particular commit. So let's just do this. So cache custody objects weekly to avoid expensive recreations. Expensive reconstruction. This patch adds a spin lock protected. Wait, is it spin lock or spin space lock? Spin lock is a word. All right, so that's spin lock dash protected. Intrusive list custody cache. It's a simple intrusive list containing all currently live custody objects. This allows us to reuse existing custodies instead of creating them again and again. Yes. This gives a pretty decent performance improvement on find slash. Yes. Okay. So I think that's okay. And then when it comes to like the invalidation of existing custodies, my understanding from other systems is that you don't necessarily need to do that, because if you open a file, say, and that file is then moved in the file system, but you still have it open, your idea of where that file exists in the file system, it's okay for that to be outdated. Like, it's okay that you believe that you open etc password, even though we have renamed it to etc password.backup or whatever. So I think that's okay. And given that we actually, the cache, the way that we set up the cache is that everything has to match, right? So it literally has to be that you're requesting to create an identical object. So this is really like a deduplication or uniquing mechanism. And the object, once created, is immutable. So you cannot change the name or inode or parent of an existing custody. So custodies are immutable, actually. I guess we should have mentioned that. So really all that you're doing here is just deduplicating it, which I think, at least within the current realm of possibilities, should not come with a behavior change. But that may be optimistic, I don't know. So anyways, now that we have done commits, let's see where we're at and then grab a profile. But I feel like we're already making good progress here. I knew that we were going to get into caching the custodies, but I was definitely not expecting the sysfs and procfs things. So it's fun when you start profiling stuff, because even though you might have some idea of what you're going to find, you usually find other stuff as well. So let's see. First, let's do some cold runs here just to warm up the machine. And look at those times, 667. That's the neighbor of the beast. Very, very good. Okay, so now we have our profile. Resolve path. What else are we doing? I guess we should dig into here, see what's going on. So custody try create is, I mean, it's still like 14%. And I wonder if that's just, is it like that we are using a list of all live custodies and that list just gets humongous? That's certainly a possibility. And once we have a better hash table solution for the kernel, because we don't have an intrusive hash table at the moment. It's something that we should have, but we do not have it yet. This would be a great thing to use an intrusive hash table for. I suppose we could put a non-intrusive hash table on the side just to make lookups faster here, but I don't know. Let's see. What else can we do though? So we go to lookup, and then what does lookup do? Lookup calls get inode. But now, like, we're in the realm of ext2fs, basically. I guess we can experiment a bit more with the custody try create. We can try to slap a hash table on this and see if that gives us more. So, what do we do with that? Where do we put the hash table? I guess we would we'll have to protect it with the thing. So like custody cache, let's say, and then let's put the list into there. Custody cache. Yeah, let's just call it cache instead. So cache. Call this all custodies. Sure. Custody cache. Sure. Cache.all custodies. Sure. Okay, and then we are free to put a hash map in here that, well, we really have to invent like a key for this. So like a cache key. Or wait, do we though? I think maybe we do. So there's a hash table of custody cache, but let's just call it hash table. We need some custom traits here so that we can provide our own hash function and stuff. So where do we do stuff like that? Okay, so let's make our own traits. Custody cache traits. And that shouldn't be a custody cache pointer, but a custody pointer. Okay, so what is the hash for a custody? Well, if it's a null pointer, then the hash is 0, sure. Otherwise, return. Well, we have a whole bunch of things here, so we need to hash the parent, and then the name and the inode. Okay, well, we can just figure out how to do that. So we'll do a parent hash of the custody parent pointer and the custody inode pointer. That's our start. Wait, do we have a putter hash actually? Yes, we do. Okay, so we have a parent hash of the putter hash of the Okay, so we're mashing together some hashes here. And then we want to mash that hash together with one more hash, which is the name of the child. There we go. So we have 3 hashes that we are combining into the Uber hash, custody hash. And then we just need to be able to compare those custodies. And maybe those need to be const, actually. I haven't made custom traits in forever, so bear with me as I remember how to do this. So the way that we figure out if they're equal is, well, if A equals B, return true if A or not B. So if either one is null, it's not a match. Otherwise, return A parent equals B parent, and a inode is the same as B inode, and a name is the same as B name, and a mount flags is B mount flags. Whew. Okay, does that even build? Let's see. Cached custody is cache hash table get Oh, wait, shoot. I can't, oh, damn it. I can't do this. This is not going to work. That's why I needed a key, because I don't have the custody pointer. I just have the inputs. So, okay, I didn't think about that correctly. Right. Okay, so we just need to define the traits for traits. Public traits. We need to come up with a key type. So cache key. And the cache key is these guys right here. Yes, 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 and yes. Yep. And let's do this for good measure. And then this becomes a hash map of cache key to custody. Sure, I'm gonna call it the map. Cache key. Wait, here we're comparing two custody things, right? Oh, no, wait. We're still comparing two cache keys. Okay. All right, and I just have to fix this up. Our Uber hash. Like that. Oh, and the map flags, we almost forgot. Okay, let's Uber hash those as well. Mount key mount flags. Boom. Okay. So now we have to make a key so that we can use it for lookups. Parent is parent. Name is name. Inode is inode. And mount flags is mount flags. That's really easy. Okay, and then if let's call it an entry. If entry has value, wait, can I not get? Why can I not get on the map? I remember hashing traits cache key. Oh, shoot. I have to say that we're using the custody cache traits, right? Yes, there we go. So if that's a match, then we return. Okay, and then we shouldn't need to iterate across the entire thing. Otherwise, we do have to add it to the map. So map set key and custody. Footer, right? Wait, does that not work? What do you not like? The copy assignment of... Oh, probably because we have a reference. Okay, fine. Let's use a pointer. I guess that was a bit weird anyway. Okay, so now we can set it. The set hash map set. Does that take R value reference? No, it takes a const reference. Okay, okay. And then when we remove a custody, we kind of have to recreate the key in order to remove ourselves from the map, which is a bit unfortunate, but it's probably the cleanest way to do it. So we'll do that. Or can we even do like name like this maybe? Yeah. Yeah. This is much better. Do I have to say? Wait, why don't you like this? Oh, because that's const. All right. Because everything is const here. Dang it. Well, I guess we can make these const. Wow, flailing up and down here, but it's gonna be okay. All right, so we've made our cache key, and then we can finally call cache map remove. Can remove this godforsaken key, and boom. Okay, let's see if this works. I have a tickling feeling that I did something wrong here, but we'll see. Yeah, at least we discover it quickly. So we're doing an equals, and then we get a bad read. Sure. Doing a bad read in equals when you're trying to do a removal with a cache key. Sure. That's kind of interesting, actually. So comparing two of these goes wrong. And who's going to be the bad guy? Well, it's probably the name comparison, right? So are we putting a temporary name? Are we storing a temporary name in the map? Oh, I guess we are. Yeah. Right. Here. We end up, when we store this key into the map, then it still has the function parameter input here. Whatever was in that argument is now stored in the key, which was probably a temporary that our caller had. So we have to actually switch that out for the permanent name key string here that we created. So at that point, we have to do key.name is name key string view. Okay, now you don't like it because I have moved that key string. Look at me. Can't be doing that. Wow. Basic C++ problems here. Okay, yeah, of course. So that's not going to work, but what if we did that right here before we move it? Because it's still in the same location. All right. So find slash dev null. Is this at all faster? 699, 687. This doesn't feel like it's faster. Also, the numbers don't say that it is, but let's see what it's spending its time on now then. What did I create here? Find 37.1. Okay. Custody try create. I mean, so we're still hidden. We don't see what's going on. We're in that spin lock. But at least iterating this list does not appear to have been the issue, because now that we replace it with a hash table lookup, it seems like it's not faster. So what I should probably have done first actually is check cache size. We just print out the current cache size at this moment. I kind of did feel like using a hash was going to be faster. But if you look at the cache size, it seems to be around 60 in steady state. And then if we do a find, yeah, it still sort of lingers around 60-ish something. And looping through 60 of these custodies, doing these checks, that's not particularly heavy. I think if we start allowing items to stay in the cache, even though they're not currently used, and the cache would be allowed to grow to, like, let's say 1,000 items or something like that, using a hash, of course, becomes much more important, because like scanning through every possible match in the cache, it's not very efficient if you can hash and only look in a couple of places. But it seems like at the moment this doesn't really buy us anything, so I think we're going to skip adding this to the code base right now, and I don't mind actually holding out for an implementation of a intrusive hash table, because that would be even nicer. Because the hash map that we're using here, it will actually do heap allocations to for its storage, and I think ideally we would have something that doesn't need to do that. Anyway. So let's see. Let's stash that, and I think I'm gonna take one more profile again and just look at it. Profile, Klook. Profiling is so much fun. I'm always in my happy place when we're doing this. So yeah, I guess it's not like obvious what to do next, and I think we've already made great progress today. So I think probably gonna end the video here, and then have to kind of regroup and look at some other avenues for improving performance here. I need to investigate, like, what would be the impact of allowing custody objects to stick around, stuff like that. But yeah, let's end it here. We made good progress, down from what was it, like 900, 1000 milliseconds down to, if we remember to time it, down to 700, 667, 680. Yeah. So definitely a huge improvement in path resolution performance and find slash performance. So I want to thank you very much for checking out the video. I hope that you saw something interesting here. and that that maybe I inspired you to look into some of these concepts or some other concepts. It's very, very nice stuff here. Anyway, thank you for hanging out and indulging me while I work on this. I will see you all next time.